Part 2. Charts, atlases, and smooth structure, building the foundations of a differentiable manifold. Let's briefly recall what Part 1 established. Many natural spaces support calculus, yet are not open subsets of Rn. The solution is to cover the space with overlapping local patches requiring smooth transitions between them. We recalled the prerequisites: topological spaces, the Hausdorff condition, second countability, and homeomorphisms. In Part 2, we will formally define locally Euclidean spaces and charts, define atlases of class C infinity with their compatibility condition, build the maximal differentiable structure, and finally define the smooth N manifold. We will work through the stereographic atlas on Sn with an explicit transition map, computation, the torus as a smooth manifold, and motivate and state the partition of unity theorem. What is the bare minimum requirement for local coordinates? Every point must have a neighborhood homeomorphic to an open piece of Rn. This gives us a way to assign n real numbers, that is, coordinates, to every point near P. It also imports a notion of continuity near P directly from Rn. But this is not yet sufficient for calculus. A homeomorphism only gives us continuous coordinates. To differentiate, the coordinate changes on overlapping patches must be smooth, and that is exactly the role of the atlas. Here is a closed wavy curve, a compact one-dimensional manifold embedded in the plane. Pick a point P on the curve and highlight a small patch around it. Zooming into that patch, the curve straightens out to look exactly like a piece of R1. Locally, the manifold is indistinguishable from the real line. The chart map phi takes the coordinate neighborhood U homeomorphically onto an open subset of R1. A locally Euclidean space of dimension n is a topological space M such that every point P in M has a neighborhood homeomorphic to an open subset of Rn. When phi maps U into an open subset of Rn, we adopt the following terminology. U is called a coordinate neighborhood. Phi is the coordinate map. The component functions xi equal ti composed with phi are the coordinate functions, where ti denotes the ith canonical coordinate function on Rn, simply the map that reads off the ith component of a point. And the pair, U and phi, is called a chart. On the left, a curved arc represents a patch U inside our manifold M. On the right, a flat real axis represents Rn, where phi maps U. Watch as a point moves along the arc. The projection rays trace its image on Rn under the homeomorphism phi. The map phi from U to its image is a homeomorphism, the fundamental building block of a chart. The definition requires U to be a connected open subset of M. This ensures that phi of U is also a connected open set in Rn, giving us a genuine coordinate system. Why does this matter? By invariance of domain, if an open subset of Rm is homeomorphic to an open subset of Rn, then M equals n. Therefore, the dimension n is the same at every point of a connected component. It is an intrinsic property of the space M. We write dim M equals n. Here are two distinct points, P and Q, sitting close together on our space. Let them drift apart so we have room to find their separating neighborhoods. We find an open neighborhood UP around PE, and a separate open neighborhood VQ around Q. The Hausdorff condition says these two neighborhoods are disjoint. They do not overlap. For every pair of distinct points in M, we can find disjoint open sets separating them. This is the Hausdorff axiom. Suppose two charts, U alpha with phi alpha and U beta with phi beta, overlap. That is, their domains have a non-empty intersection. Then a function f from M to R has two local coordinate representations on that overlap. Namely, f alpha equals f composed with phi alpha inverse, and f beta equals f composed with phi beta inverse. They are related by f alpha equals f beta composed with the transition map, phi beta composed with phi alpha inverse. F alpha is C infinity if and only if f beta is C infinity, provided the transition map is C infinity. The atlas axiom imposes exactly this condition on every overlapping pair of charts. Given two charts with overlapping domains, the transition map from chart beta to chart alpha is phi alpha composed with phi beta inverse, a map from phi beta of the overlap to phi alpha of the overlap. Three things to notice. First, the transition map lives in Rn, so asking for C infinity smoothness is completely unambiguous. Second, it is invertible. Its inverse is phi beta composed with phi alpha inverse. Third, if both transition maps in each direction are C infinity, we say the charts are smoothly compatible. Here is the manifold M as an ellipse. Two overlapping patches share a green intersection. The chart maps phi alpha and phi beta project these patches down to Euclidean space. The images of the intersection inside each chart land in copies of Rn. The transition map phi alpha, composed with phi beta inverse, connects these two Euclidean images. The atlas compatibility condition demands this map be C infinity. An atlas of class C infinity on M is a collection of charts satisfying two conditions. Condition 1, coverage. The union of all coordinate neighborhoods is all of M. Condition 2, C infinity compatibility. For every pair of indices, the transition map phi alpha composed with phi beta inverse is C infinity on its domain. When the intersection of U alpha and U beta is empty, condition 2 is vacuously satisfied. Disjoint charts impose no compatibility requirement. Here is the ambiguity problem. Two different atlases can define exactly the same smooth calculus on M. Consider R1. Atlas 1 uses the identity chart. Atlas 2 uses the cube root map. The transition from Atlas 2 to Atlas 1 is x cubed, which is C infinity. But its inverse, x to the 1/3, is not differentiable at 0. Therefore, these two atlases are not compatible. They define genuinely different smooth structures on R. The correct notion is equivalence of atlases. Two atlases are equivalent if their union is still a C infinity atlas. Each equivalence class is uniquely represented by its maximal element, the atlas that contains every compatible chart. A differentiable structure F of class C infinity on M is a C infinity atlas satisfying coverage and compatibility, and additionally maximality. If any coordinate system U with phi is smoothly compatible with every chart already in F, then U with phi must already be in F. In other words, F contains every chart smoothly compatible with all charts it already contains. Every C infinity atlas A is contained in a unique maximal C infinity atlas, denoted F of A, obtained by adjoining all charts that are C infinity compatible with every chart already in A. F of A covers M since A is already contained in it. Any two charts in F of A are mutually compatible. We route through charts of A as intermediaries and apply the chain rule. Maximality follows by construction, and uniqueness is immediate. To specify a smooth structure on M, it suffices to exhibit any C infinity atlas. The maximal differentiable structure is then uniquely determined. A topological manifold of dimension n is a topological space M satisfying three axioms. 1. M is Hausdorff. Distinct points have disjoint open neighborhoods. 2. M is second countable. It has a countable base of open sets. 3. M is locally Euclidean of dimension n. Every point has a neighborhood homeomorphic to an open subset of Rn. Why impose these two extra axioms? The Hausdorff condition ensures limits are unique, and smooth functions can separate distinct points. Second countability implies paracompactness, which is the topological condition needed to construct partitions of unity. A smooth n-manifold is a pair, M and F, consisting of a topological n-manifold M together with a C-infinity differentiable structure F on M. We will denote the pair simply by M with the differentiable structure F understood. Here is the full logical chain of structure. We start with a topological space, giving us open sets and continuity. Add Hausdorff and second countability to obtain a topological manifold, which is locally Euclidean. Then add a C-infinity atlas, and we arrive at a smooth manifold, where calculus is possible. The simplest example of a smooth manifold, and the model for all others, is Rn itself. Hausdorff. Distinct points are separated by disjoint open balls. Second countable, balls with rational centers and rational radii form a countable base. Locally Euclidean, Rn is itself an open subset of Rn. Atlas. The single chart consisting of Rn with the identity map. Transition map is the identity itself. A function from Rn to R is smooth in the manifold sense if and only if it is smooth in the classical multivariable calculus sense. The abstract definition recovers exactly what we already know. Every open subset U of Rn is a smooth n-manifold, with the single chart atlas given by U together with the inclusion map into Rn. Hausdorff and second countability are inherited from Rn. Local Euclideanness is clear since U is itself open in Rn. The single chart trivially satisfies compatibility. There are no overlapping pairs. The open n-disk, the upper half space, and the general linear group GLNR as an open subset of the space of n by n matrices. The n-sphere Sn is the set of all points whose coordinates have norm equals 1, equipped with the subspace topology. Sn is Hausdorff and second countable. It is also compact by the Heine-Borel theorem. Our goal for the next 3 slides: define a C-infinity atlas on Sn using 2 stereographic projections, and verify explicitly that the transition map is C-infinity. This is the first non-trivial atlas computation in the course. Here is S1, the circle, standing in for Sn in our geometric intuition. Mark the north pole n at the top and the south pole s at the bottom. The equatorial axis represents Rn, the target of our stereographic projection. Watch point P move around the circle. A dashed ray from the north pole through P hits the equatorial axis. That intersection point is phi n of P. As P approaches the north pole, the image races out to infinity, which is why n must be excluded from the domain. The formula phi n of x equals 1 over 1 minus xn plus 1 times the vector of first n coordinates. Let n be the north pole, the point with 0 entries except the last entry 1 in Sn. The stereographic projection phi n maps each point P in Sn minus n to the intersection of the line through n and P with the equatorial hyperplane where xn plus 1 equals 0. For the explicit formula, parameterize the line as n plus t times P minus n and solve for xn plus 1 equals 0. This gives t equals 1 over 1 minus xn plus 1. The resulting formula is phi n of x equals 1 over 1 minus xn plus 1 times the vector of first n coordinates. This is a homeomorphism from Sn minus the north pole onto all of Rn. The south pole projection is defined analogously. Let S be the south pole, the point with 0 entries except the last entry negative 1. The projection phi s maps each point P in Sn minus s to the Rn via the line through S and P intersected with the equatorial hyperplane. The formula is phi s of x equals 1 over 1 plus xn plus 1 times the vector of first n coordinates. Un is Sn minus the north pole, and Us is Sn minus the south pole. Their union is all of Sn. These two charts cover the sphere. The overlap of the two charts is Sn minus both poles, and phi s maps this overlap to Rn minus the origin. We want to compute the transition map phi n composed with phi s inverse, a self-map of Rn minus the origin. Step 1. Invert phi s. Given u in Rn minus 0 with norm squared equal to the sum of squared components, the inverse is 2ui over norm u squared plus 1 for the first n components, and 1 minus norm u squared over norm u squared plus 1 for the last component. Before we continue, let's briefly recall the mapping for phi n, which scales the first n coordinates by 1 over 1 minus xn plus 1. Step 2. Apply phi n to phi s inverse of u. The last coordinate of phi s inverse of u is 1 minus norm u squared over norm u squared plus 1. Calculating the denominator, 1 minus xn plus 1 equals 2 norm u squared over norm u squared plus 1. Inverting this gives us the scaling factor, norm u squared plus 1 all over 2 norm u squared. Applying the scaling factor to the first n coordinates, we get phi n composed with phi s inverse of u. The scalar terms and the 2's beautifully cancel out, simplifying strictly to u over norm u squared. In conclusion, the transition map is an inversion in the unit sphere, which is C infinity. The proof for the reverse transition map is exactly analogous. Therefore, we have shown that all transition maps on Sn are smooth, forming a valid C infinity atlas. With the smooth structure in hand, we can now define what it means for a function on a manifold to be smooth. A function f from M to R is smooth if, for every chart U with phi in the differentiable structure, the composition f composed with phi inverse is C infinity in the standard sense. If f composed with phi alpha inverse is C infinity in one chart, then for any other chart, phi beta, we have f composed with phi beta inverse equals f composed with phi alpha inverse, composed with the transition map, phi alpha composed with phi beta inverse. The chain rule then gives C infinity, so smoothness is chart independent. Here is a fundamental construction problem. Suppose we want to put a Riemannian metric on M, a smoothly varying inner product on each tangent space. Locally, in each chart U alpha with phi alpha, the Euclidean metric pulls back to give a perfectly good metric G alpha on U alpha. But on overlapping charts, G alpha and G beta generally disagree. A naive average is not globally well defined. The solution is the partition of unity. We find smooth functions psi alpha from M to the interval 0, 1, supported in U alpha and summing to 1 everywhere. The psi alpha are the partition of unity. Let us visualize a partition of unity on M. Here is psi alpha, a smooth bump function supported in U alpha. Here is psi beta, supported in U beta, and psi gamma, supported in U gamma. Notice the bumps overlap. Despite overlapping, the bump functions are carefully normalized so that their pointwise sum equals exactly 1 everywhere on M. This is the partition of unity condition. Each function psi alpha has its support contained in the corresponding chart domain, U alpha. A partition of unity is assembled from bump functions, smooth functions that are compactly supported and identically 1 on a smaller inner set. Mathematically, we define a bump function ρ to be exactly 1 inside some radius r. It then drops off until it hits exactly 0 outside a larger radius capital R, keeping its value smoothly bounded between 0 and 1 everywhere in between. To actually build one of these, our key ingredient is a special function of one real variable, h of t. It is defined as e to the negative 1 over t for positive t and identically 0 otherwise. Because all its derivatives vanish at 0, this function is C infinity everywhere. We form our actual bump functions by carefully combining shifts and scales of this exact function. Now that we have our local building blocks, the bump functions, we need a global strategy to glue them together. This requires us to look at how we cover the manifold. A covering of M is a collection of open subsets whose union is all of M. A covering is locally finite if every point in M has a neighborhood that meets only finitely many of the sets U alpha. For the partition of unity sum over alpha of psi alpha of P to be finite at every point P, we need all but finitely many psi alpha to vanish at each P. The natural question is, can we always construct such a cover for any manifold? This leads us to the concept of paracompactness. A Hausdorff space M is paracompact if every open covering admits a locally finite refinement. A locally finite covering where each set V beta is contained in some U alpha. Any locally compact Hausdorff space with a countable base, in particular any topological manifold, is paracompact. Consequence, every open cover of a topological manifold can be refined to a locally finite cover. Combined with bump functions, this is precisely what allows us to construct partitions of unity on any smooth manifold. Equipped with these tools, bump functions for local control and paracompactness for global structure, we can finally state our main goal. Here is the partition of unity theorem. Let M be a smooth manifold and let U alpha be a locally finite open covering with each closure of U alpha compact. Then there exist smooth functions psi alpha on M, satisfying condition A. Each psi alpha has compact support contained in U alpha, and condition B. Each psi alpha is non-negative, and the sum over all alpha of psi alpha of P equals 1 at every point P. Such a family is called a partition of unity subordinate to the covering. Stating the theorem is one thing, but how do we actually build such functions? The construction has 3 steps, and step 1 is to construct local bump functions. For each alpha, choose a compact set K alpha inside U alpha such that the union of all K alpha is M. With these compact sets in hand, our goal is to construct a smooth function psi alpha tilde from M to 0, 1 that equals 1 on K alpha and has support contained in U alpha. This is exactly where our earlier work pays off. Work in the chart U alpha with phi alpha. Take a classical bump function on Rn, adapt it to the image of K alpha inside the image of U alpha. Pull it back to M via phi alpha inverse. Extend by 0 outside U alpha. We now have a family of bump functions, one for each chart, but they don't yet sum to 1, so they aren't a partition of unity. Step 2 fixes this with a normalization factor. Define the sum psi of P to be the sum of psi alpha tilde of P. 2 things make this sum well behaved. The sum is finite near every point, so psi is C infinity. And since the K alpha cover M and psi alpha tilde equals 1 on K alpha, we have psi of P at least 1, and in particular strictly positive everywhere. A strictly positive denominator is exactly what we need. So for the final step, we define the partition of unity by dividing through. Set psi alpha of P to be psi alpha tilde of P divided by psi of P. And this gives us everything we wanted. Each psi alpha is smooth. It is a ratio with strictly positive denominator, supported in U alpha, and the sum over alpha of psi alpha of P equals psi of P over psi of P, which is 1. With the construction complete, it's worth pausing to see why we went through all this trouble. Partitions of unity are the central tool for passing from local to global constructions on a manifold. The first place this shows up is Riemannian metrics. Given local metrics G alpha in each chart, U alpha, we form the global metric G equals the sum of psi alpha times G alpha, which is globally smooth and positive definite. The same idea carries over to integration on manifolds. The integral of a form omega over m equals the sum of integrals of psi alpha times omega over each U alpha. And each term is a classical integral on an open subset of Rn. And more generally, this is how we extend local sections. Locally defined smooth objects, differential forms, connections, can be patched together globally using the psi alpha as weights. Let us summarize what Part 2 has established. We defined locally Euclidean spaces where every point has a neighborhood homeomorphic to Rn. A chart is a coordinate neighborhood together with a homeomorphism to Rn. An atlas of class C infinity is a covering family of mutually compatible charts. A differentiable structure is the maximal C infinity atlas, the unique canonical representative of its equivalence class. And a smooth manifold is a Hausdorff, second countable, locally Euclidean space equipped with a differentiable structure. The key tool introduced was the partition of unity, the fundamental mechanism for all local to global constructions in differential geometry. Coming in Part 3, smooth maps between manifolds, the differential, the notion of rank, immersions, embeddings, submersions, and the major structural theorems.